slope field, it actually can be used to check answers. In fact, if you make a connection as we go through this lesson, you'll realize that. You'll realize that a slope field, in some sense, actually gives you the answer before you get the answer. That'll be interesting for you to try to navigate that. Okay, now, don't worry, as I said, it's not that you have seen this before, so we're all kind of at the same place right now. Probably want to just jot this down. I don't like the way it's formatted up here. You probably want to write it like a fraction, write it as like 1 over x. And then the other one, it's not written real well up here on the screen. Let me just write it the way that it really should look. It's 1/5 x. So I apologize if you weren't sure about the second part of that. So it's 1 over x minus 1/5 x. Okay, but I think something we can all agree with is that, well, can you agree with me on this? That's a differential equation. I mean, you can sound like really smart. You can go home and say, hey, Mom, we were talking about differential equations. I mean, it just sounds like, you're doing some tough stuff. And it can be some tough stuff. But we want to understand, first of all, that a differential equation is what it was back in the beginning of the year. Even though I didn't use that word, remember, it's a derivative. It's a slope formula. Make sure that you let that sink in a moment. A differential equation has always been, a derivative has always been a slope formula. It was kind of the first thing that we said about a derivative, because we all understand formulas. You can plug into them. Now, here's the interesting thing, and we're going to do this in about 5 seconds, but we're going to plug into this slope formula. We're going to plug in, and we're going to find slopes. The question is, of what? I'm not answering that yet, but just realize we're going to plug in, we're going to find slopes, but you should kind of be wondering, of what? Like, what are these slopes of? Okay, let's do the easy part. Let's plug in. You say, what do you mean plug in? Well, x values. Okay, now we're just going to kind of do this mentally. Some people will punch this in their calculator, but most of the numbers I'm showing you, you don't need to plug in your calculator. If you plug in 1, you get 1 minus a fifth. 1 minus a fifth. So I already gave you the answer, but it's 4/5. Now that means that x equals 1, there is a slope of 4/5. Now that little dash I drew right there is trying to represent a rise of 4 and a run of 5. In other words, a slope of 4/5. You'll see, but just kind of go with this a little bit. Let's plug in another number, plug in 2. Again, you don't have to do that on a calculator. I kind of already did it, but if you plug in 2, you get a half minus 2/5. A half minus 2/5 is a tenth. That means that x equals 2, we have a slope of 1/10. And I, at least from an algebra class, used to say that 1/10 is not as steep. 1/10 is not as steep. So I'm trying to draw a line that represents a slope of about 1 over 10. Basically, again, it's not as steep. How about x equals 3? X equals 3. Negative. Okay, well, negative 4 over 15. Well, it's negative, so it's got to be tilted negatively. It is just a sketch. If you're like, how do you know how to draw these? I'm just trying to do my best to kind of compare them. Because look, if you look at the next one at 4, I get negative 11 over 20, which is steeper. It's steeper. So just try to draw it steeper, and you're going to see something in a moment. You're going to see that what we're making is a slope field. You're going to see that we're making literally a field of slopes. But let's go to the other side of of the graph. Let's go to the negative x values. Now, if I plug in a negative x, maybe -1, -2, -3, and -4, just kind of going through that a little more quickly, you can see that we just get the opposite of each of those. Just get the opposite. It's not a bad idea to write these down. It's always a good idea to have record of what we're doing, but realize that as I try to draw these slopes, I'm drawing a slope that is -4/5. I'm drawing a slope that's -1/10. Basically, I'm trying to draw some little lines that have those little slopes. 4/15, 11/20. And I'm trying to draw the lines to be a little steeper as I move along there. Now, even if you truly don't have much of an idea of what is happening here, although I did say we're making a field of slopes, you might realize that the position of these little line segments, well, can't be determined. There's absolutely no reason I would know where to put these little line segments in sort of a y reference, which is why I could have an equal argument that any one of these little line segments that could be at a different y reference. And continuing, I could take, again, each one of these little slopes, and I could say, but it could be here, but it could be here. A little better. dy dx is a differential equation. It stands for the derivative. It gives slope formulas, or it's a slope formula, so it gives slopes of what? We have these slopes of what? Probably will want to play along here. I'll fill you in that we're going to do something with those programs that I sent out some time ago. If for some reason you don't have them, you didn't bring a calculator, whatever, just relax. I can give it to you again, but I'm going to go ahead and go through this. And again, just adjust depending on how you're prepared or what you have. There's a program that is able to draw what I am trying to draw behind the screen. And we're going to show you how the calculator can draw these basically much faster. To run the program, or to understand the program, the first thing we have to do is we have to use the y equals screen as a storage spot. You kind of heard me say this before. It's a little strange though, because when I'm actually typing in the y equals screen, it's not a y equals equation. Depends on how deep you want to get so far, but I like to tell this truth because it can confuse some kids. In a few minutes, they'll be like, wait a minute. So I'm typing in the derivative into the y equals screen. Basically, it's a storage spot for the program. Right? All of you will realize why I'm making a big deal out of that in a moment, but all you have to do now, all you have to do is, at this point, push your program button. Again, if everything's still there and you're all good, you should see on option 4, a strange spelling of slope field. It's because you can only use so many characters in a title. So mine is option 4, slope field. Give her a run. Either watch mine or watch yours. I'll have to give you some programs there. We'll give it to you. You may want to just change the window, and then you have to run the program again. Just kind of consumes standard. That one got me. I'm not sure I'll have to figure it out. I'm not seeing it. 1 over x minus 1/5 x. We'll type that in. Now, those of you that it worked, cool, you look on your calculator. Even if it didn't work, you can look up here and we can continue to learn. Because what this shows is all the potential places, at least within -10 to 10, all the potential places for these little line segments. And we call this a slope field. Okay, we'll give kind of a formal definition in a moment, but the slope field is trying to say something to you. You just have to listen. In fact, you more have to see, you have to look. And it's trying to show you slopes, but again, of what? Now, x equals 0, I never plugged it in, but I want to make sure that we point out that there is no slope there. It's just something to put in the back pocket. There is no slope. Before I show you the next little nugget here, I kind of wonder, do you feel like you see, this is technical math jargon, do you see the flow of this slope field? Do you see the line that might be able to pass through these line segments? Do you see the way these slope fields are trying to show you a particular solution? Okay? It might be a little easier to see it if we pick a point, or in this case, if you're given a point, on this slope field. Now, that would represent point 1, 2. I have the ability to write on my calculator because I can erase it easily. So I'm just going to sort of plot the point 1, 2. Maybe you're choosing to put it on your notes. But here's kind of the big connection, at least right now for this lesson. If you take that point as, so to speak, as a starting point, and if you go with the flow of the slopes that are near that point, we can make a pretty good argument that we can draw a line, or that the line that I drew here would match those slopes. In a similar fashion, I can continue this line actually on the other side and say the same thing. The big question again is, what is that line that I drew? What is that line that I drew? It seems to go with the flow of those line segments. Let's go back over to where we started, dy dx. I hope you did a nice job with this in your assignment, but again, I'm going to grade it and have a look. But something you should have done when you had an equation of the form dy dx equals is you should have solved it, plus you for the original equation. Now remember, when you have a differential equation and you do its antiderivative, you actually get the original equation. Let's do the antiderivative so we can solve this differential equation. Now 1 over x, there's never a bad time to talk about that. I hope you're catching on. That's a rule. It's the natural log of x. You'll notice that I keep putting those absolute value signs around it. Technically, that is officially sort of an always. It's always the absolute value because you can't do the ln of a negative number. So we'll use the absolute value symbols. Now this guy over here, don't get too fancy with me. It's just a power function. If you add to the exponent, you're now going to have an exponent of 2. And if you divide by that new exponent, well, that gets a little clunky because I already have a fraction. But I add to the exponent, I divide by it, and we end up with 1/10 of x squared. We end up with 1/10 of x squared. Plus c, of course. And our little field connection is just a step or two away. Now, if I had told you that y sub 1 equals 2 in the homework problem, and you would solve your differential equation, but you were given, then you would have been able to continue to solve for the c value. We call it an initial value problem. So I'm going to go ahead and run with that, because I can plug in 2 for y, I can plug in 1 for x, and again, although we have some interesting numbers here when it kind of boils down to it, some of you did get this marked wrong on your test because I had mentioned that I want you to know this. So just saying it nicely again, the ln of 1, it's nice to know that that equals 0. It really makes your answers more accurate, and it's mathematically true. But basically, I end up adding a tenth to the other side. I add a tenth to 2, and we get 21 tenths as a fraction, which is never a bad way to write the answer. So, what do we have here? We have something that you've seen before. We have the solution to a differential equation. Again, the natural log of the absolute value of x minus the 10th x squared plus 21 tenths. That's the solution to that differential equation. Notice that it's y equals. We go over here and we remember that we created this field of slopes. And as I've said a few times, slopes of what? Slopes of what? Again, try to see the big picture of mathematics. The first half of the year, we started with y equals, and we get dy dx equals. That obviously means that this derivative gives the slopes of this equation. Now, though, we started with the derivative, and we went back to the original equation. But it's the same answer. This derivative gives the slopes of this equation. This slope field gives the slopes, visually, of that equation. And you get one try to sort of prove it. I'll show you what I mean by that, but I'm going to type in the actual log of absolute value of x. I'm going to type in this solution. It's a little fancy because it uses absolute value. Absolute value is in the Math Num menu. But the big idea here is you want to realize I'm typing in this solution. Again, it's a little fancy to type in because of the absolute value. The reason I say you get one chance is because what's going to happen next, assuming I typed it in right, is that it's going to graph this y equals equation. And where is it going to graph it? Right on top of that slope field. However, I only get one try to graph the equation before the slope field disappears. What that means is if you made a mistake, you typed something wrong, whatever, it happens all the time, you have to do the slope field program again. Okay. I'm also going to make my line thick because I know there's a lot of commotion on the graph. Let me erase this so we can see. So we can literally see the solution go with the flow of the slope field. Again, we see the solution go with the flow of that slope field. And we look at that and it should say yes, or it's right, or it's connected. And of course, again, the connection is the derivative matching up with its original equation. What do you think? I have some stuff to show you. Just kind of wondering as we go slowly the first time thoughts. And that's when you just need the program in the back of your calculator. We'll get on there. Here's some things that have been said. As we often say, though, it's helpful to see it. When you see it, sometimes you understand it. That's what we're going for here. So a slope field is a plot, or a lot of plots, of short line segments. They have the slopes that come from the dy dx formula. We did do this by hand. We drew one by hand. I'll let you know that normally it's a calculator that draws it for us. Here's the big thing, though, the big takeaway. Trying to keep it as short as possible, but you gotta understand what the slope field is showing you. It enables you to see the solution. That is, it enables you to see the original equation. You know, the y equals. So we actually could see what it looked like before we found it. Of course, once we found it, we were able to graph it and essentially check it to make sure that it really does go with the flow. Again, your slope field is basically a visual solution. Now remember, we're using different words. And if you're really thinking, which is why I'm going slowly here, I don't want to go too fast. All of this is the antiderivative. So in a sense, the slope field shows you the antiderivative. It shows you that solution. You know, maybe you're asking, hey, it sounds good, but you know, what do I need this for? Well, I'll show you. Okay, I'll show you. It'd be better though to do that in a fuller period where we can make a couple connections. So when you guys come back,